These are the frequently asked questions for Algebra 2, Section 8.4, Day 1. Starting with number 9 up here. It says, simplify each rational expression, state any restrictions on the variables. And we have a 2x in the numerator. And the first thing you want to ask yourself about this denominator is there a common monomial factor? And hopefully you're saying, yes, there is, because we can take a 2 and an x out of that binomial. And you can think of it either as dividing, so 4x squared divided by 2x would be 2x, or you can think backwards. 2x times something gives me 4x squared. And go ahead and do the same thing for the negative 2x in the back. Either think of it as division or think 2x times something gives me the negative 2x, and that something is 2x minus 1. Now, we definitely can see that the 2x will cancel out. And so this will reduce to 1 over 2x minus 1. But the whole reason that we leave everything so that we can see it is for those restrictions. Remember, restrictions are like domain. We want to say what values we can't use. And those values for fractions would be anything that have us dividing by 0, because dividing by 0 is undefined in mathematics. So the first 0 that we have here will come from 2x equaling 0, and by dividing by 2, of course, we get x equals 0. So x cannot equal 0. And then the other would be when 2x minus 1 equals 0. Well, if you add 1 and divide by 2, you get x equals 1/2. So x can't equal 0, and x cannot equal 1/2 would be our restrictions. So answer and restrictions. Number 13, you should notice, at least I hope you do right away, that what we have in our numerator on the top of this fraction is all backwards. So the first thing you would want to do is put that in the correct order, put it in standard form. And then you'll notice, wait a minute, that first term has a negative in front of it, and we don't leave that when we're trying to solve things by factoring. So what we're going to do is we're going to go ahead and pull a negative 1 out of that. And that, of course, will change all the signs in that trinomial. And then we'll factor and see what happens. So we have our negative 1, and I notice that 12 in the back is not a perfect square, so don't need to bother trying to see if that's a perfect square trinomial. But I need two numbers that multiply to negative 12 and add to 1, and that's going to be plus 4 and minus 3. And then in my denominator, again, I notice the 15 in the back. There is no common monomial factor. That'd be the first thing to check. And then the 15 is not a perfect square. So then we need to come up with two numbers that will multiply to positive 15, but add to negative 8. And that's going to be negative 5 and negative 3. So now we want to go ahead and cancel, but you don't want to make it so you can't see what's going on anymore. And that's because we still need to talk about restrictions. So our numerator would be negative 1 times x plus 4 over x minus 5, or negative x plus 4, negative parentheses x plus 4 over x minus 5. And if you're thinking, well, why leave the parentheses there? Because it shows we knew what we were doing. We knew to factor out a negative of that before we tried to do any canceling. And then restrictions. So you want to go back to the factored form of your denominator, which would be right here, and you realize that you can't use 5 and you can't use 3. And the reason we can't use those two numbers is because they will make us divide by 0, which in mathematics is undefined. So x will not equal 5, and x will not equal 3. Next up, we have 15. Now, with 15, several different ways to go with this one, but for most people, what's going to bother us right away is that they left a negative exponent. We know that part of simplifying is getting rid of the negatives. So what we will probably want to do with that is just move it to the upstairs right away, move it to the numerator in order to get rid of the negative. And the 10 does not have a power of negative 2, it has a power of 1, so that's going to stay in the denominator. And then, as I've talked about in class, sometimes when these get very involved, It's easier just to go ahead and multiply all your numerators and all your denominators together and see what you have instead of trying to cancel all over the place and keep track of everything. So numerator times numerator here, 2 times 5 would be 10. X to the fourth and nothing else is x to the fourth, and y squared and y to the third will give us y to the fifth. And on the bottom, 10 times 4 would give us 40, x to the third. Now, it's all one fraction. Pretty easy to keep track of everything if you do your canceling. And you could either say for the x's, the powers for division there, you're going to subtract, or you could just cancel 3 of them out from the top and the bottom, and then, don't lose track of anything. On the top we have an x and we have y to the fifth, and then on the bottom we just have a 4 left for that one. So, like I said, lots of different ways to go after, but what you need to do is keep track of your variables. And then restrictions on the domain. So let's go back to the beginning where we had a y in our denominator and an x in our denominator, which brings us to the question, but wait a minute, that originally was a y to the negative 2, which meant it was really supposed to be on the top, but it wasn't. That's the key. It wasn't on the top. And if a person were to put 0 in there and raise it to the negative 2 power, anything to the 0 power is still going to be 0. So x cannot be 0 and y cannot be 0. Then number 17. Number 17 has us multiplying, but this time we have binomials. So what we want to do is look for those common monomial factors. 2x plus 12, we can take a 2 out of that, and that will leave us with x plus 6. 3 times x minus 9, or 3x minus 9 is 3 times x minus 3. When you factor that, factor a 2 out of this numerator, and you'll get 3 minus x. And then on the bottom, we have 3x plus 8, and there's nothing we can do with that. There is no common monomial factor that we can pull out. Now, hopefully you've noticed that these two are backwards. And again, how you fix that is by multiplying it or dividing it by a negative. So on the top, we still have our 2 times x plus 6. I'm going to keep this denominator exactly as it is, but now I'm going to change that to a negative 2 so that I can reverse those. Because now I will have an x minus 3 in a numerator and a denominator, which means that it can be canceled out. So those will be gone. And then what we need to do is check and see if there's anything else that will cancel. Nothing there. So our numerator is going to be 2 times negative 2, which is negative 4, times x plus 6. And our denominator is 3 times the quantity 3x plus 8. And then go after your restrictions. Our restrictions, let's take a look at our denominators. Right here and right here in factored form. So x cannot equal 3. And then you probably, well, some people anyway will actually want to set this up so you can see where the other one is. I mean, we have 3x plus 8, and we know that if that equals 0, that's a problem. But most of you, I know, will get to this point and go, hey, it'll be negative 8/3, because we'd subtract 8 from both sides, and then we would divide by 3. So that's our other restriction right there. So again, really important to factor these, not just for simplifying, but so that you can notice those restrictions. I'm going to clear some space here and go through number 18. So number 18, again, your first focus should be on anything where you can pull out a common monomial factor. And you'll notice with this fraction, we can take an x out of that. The numerator of that one, nothing we can do, that's x plus 1. Now we go to x squared minus 4 and x squared minus 1, and no, there's not a common monomial factor, but that is a special pattern. That is the difference of 2 squares. So x squared minus 4 is x plus 2 and x minus 2. And then x squared minus 1 is x plus 1 and x minus 1. And now, of course, we're interested in reducing or cross-reducing and canceling whatever we can here. So the x plus 1s will be gone, and x plus 2 will be gone. And in our numerator, we are left with x minus 2. And in our denominator, we have an x. Don't forget about that little x. And x minus 1. And then we need to talk restrictions. Go back to the first factoring that we did right here. And anything that would make that denominator equal to 0 is out. So x cannot equal 1, x cannot equal negative 1, x cannot equal 0, and x cannot equal negative 2. All four of those would give us a 0 in our denominator and make us divide by 0, which we know we cannot do. Now, I went to the review again before there were any more of these. All right, so 56. Find the vertical asymptotes and holes for the graph of each rational function. Well, they come from the denominator. Anything that would make a 0 down there is a point of discontinuity. So I can see that x equaling negative 3 and x equaling 4 will be a problem. But then you have to figure out which ones are holes and which are going to be asymptotes. Anything that cancels is a hole. So we will have a hole at x equals 4. But we will have a vertical asymptote at x equals negative 3 because that one would not cancel out. Then 58, 59, and 60. I had to put these on because logarithms are so much fun. We'd do our little snail shelling to the x equals 1 over 32. And then a couple of different ways to take it from here. You could just think through it and say, okay, if I need a 1 on top, that's a reciprocal. That comes from a negative power. And then I have to raise 2 to some number to get 32, and that something is 5. Or you could do this, 2 to the x equals 2 to the negative 5th, and then go from there. And that would be x equals negative 5. So getting those common bases is also another way to do this. Any way you do it, your answer is going to be negative 5. Now 59, that's a fun problem. First thing I would want to do is get one base from that 5 square roots of 5. So 5 is 5 to the first, and 5 square root of 5 is 5 to the 1/2. So this is really logarithm base 5 of 5 to the 1 plus 1/2, which would be 3 halves. Now, those are inverses of each other, and your answer is 3 halves. That, I think, is the easiest way to do that, and it's also a great example of working with those inverse bases there. And then this last one, we have logarithm base 16 of 8 equals, let's look at that one this way. And hopefully you're thinking, okay, is there a base that 16 and 8 will both use? And that answer is yes, and that base is a 2. 16 is 2 to the 4th, and 8 is 2 to the 3rd. So power to power tells us to multiply those powers together, and that means that 4x would equal 3. If we divide both sides by 4, x will equal 3/4. And that will be our power for number 60. And let me take a peek here, but I believe, oh no, I'm going to do one of the solving ones here. Number 62 says solve and check for extraneous solutions. So we have the square root of the quantity x plus 1 minus 5 equals 8. First thing we would do is add 5 to both sides. So the square root of x plus 1 equals 13. Then we would square both sides so that x plus 1 equals 13 squared, which is 169. And then subtract 1 from both sides and get 168. And again, we would want to check with these because we're working with even roots and even powers here, so we would want to check and see that this is going to work. 168 plus 1 is 169. The square root of 169 is 13. 13 minus 5 is 8, so this one works. But again, important that you check your answers for 61 to 63. to make sure that if you found an answer, that it is the correct answer. Then, number 67, add or subtract, it says. And in 67, we see we have two denominators. The denominators there are 12 and 45. So we start thinking, what on earth could we use for a common denominator for 12 and 45? Well, you could make factor trees and go down and see what they are at their base and then build it back up. Or you could sit and take a look at all of the multiples that you have of numbers. So basically, we know 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36, and you just keep building up here as you go. So we've got 12 times 5, which is 60, and then 12 times 6, which is 72, 12 times 8, etc. But what it really comes down to is you see that you're spending an awful lot of time finding multiples, and you get over here to 45 and it's 45, 90, and you've got a ton of things that you still need to check for with the 12. So let's break this down with the factor trees, because that choice seems to be the one that's going to be the shortest amount of time spent on this problem. So 12 is 3 times 4, and then 4 is 2 times 2. So as the prime factorization, that's going to be 2 squared times 3 for 12. Then for 45, most people will think of 5 and 9 right away, and then 5 would be 5, but 9 would be 3 and 3. So that's going to be 3 squared times 5. So to find that least common multiple, what we need to do is take every base, and we have to take it to its highest power. So we have a base of 2, and that's the highest power to the second power there. And then we have 3 to the first and 3 to the second, so we'd have to take the 3 to the second. And then we'd have to take the 5. So our least common multiple for these would be 4 times 9 times 5, which is 180. So doing this by hand, you would want to use a least common denominator of 180. So we'll take 180 and divide it by 12, and that means we're going to have to multiply the numerator and denominator of 11/12 by 15 in order to make this work. So 15 times 11 gives us 165 over 180. And then we need the 7 over 45 to be something over 180. So if we take 180 and we divide it by 45, we're going to get 4. So we need to take our numerator and our denominator by 4. And finally, we'll have 165 over 180 minus 28 over 180. So that is 137 over 180. Or you grab your graphing calculator and you punch those fractions in, and then you use the math button to convert it back. But what we're going to be doing in the next section requires that we are able to figure out the least common denominator, and that's what these problems were all about, was finding that.